What's up, everyone? Today we're going to do something a little bit special from what we usually do most of the time. So as you can see from the board, we have 4 different numbers. What we're going to do is we're going to try to put them in a decreasing order, meaning that we will find the largest amount of all 4, and then we're going to find the second largest, so on and so forth. But of course, we are not going to use calculators, otherwise it will be very easy and it also defeat the purpose. So what are we supposed to do? Well, first we're actually trying to use the high school algebra method to figure it out, and then we're going to move on and talk about something more general and use the calculus parts to help us develop the ideas. Are you ready for it? Here we go. So let's take a look here. For the 4 numbers, what do we see in common? Well, let's take a look. For the first number, we have 2 times 18. The second number is 5 times 15. The third number is 13 times 7. And the last number is 14 times 6. So perhaps you cannot tell it right away. But what if we try to add the 2 numbers instead of multiplying them? What do we get? Well, if we take a look at the first number and add the 2 numbers that we're multiplying by, we actually get 2 plus 18, which is giving us 20. Similarly, we have 5 and 15 here. If we add them together, we also get 20. So on and so forth. How does that help? Well, here we can actually think it as a geometry problem or a high school algebra problem, which is, suppose we have 2 values, a and b, and we know that their sum is actually the same. In this case, they're all equal to 20. Then now we want to find out that which a times b, which is the options that we have, will give us the biggest value. How do we do that? Well, geometrically, we can think it as a square or a rectangle, where a could be our length, and then b would be the width here. So that we know that the length and the width together will actually give us a fixed number, 20. In other words, we can actually fix the perimeter of this rectangle to be twice as much as the number we have, which is 40. Now, in a given perimeter, how do we find the largest area? Again, why do we want to find the largest area? Because we know the area of a rectangle is length times width. In this case, it will just be a times b, which is what we want. Then, if we go back to high school algebra or in geometry class, we claim that with the fixed area of a rectangle, with a fixed perimeter of a rectangle, the area will be the largest if the length and the width of the rectangle to be the same. In other words, we can say that we get the maximum area if the rectangle is a square. So in this case, we say that area, which is equal to length times width here, or in our case will be a times b, is actually the biggest if a and b are the same. In this case, we will say that the biggest area will be 10 times 10, which is 100. So it means that if we can get as close to 100 as possible, that number will be the biggest. And how do we know that the number is getting closer and closer to 100? We also can think that these 2 values have to be as close to each other as possible. So what we can do now, we can just look at the difference between the 2 numbers of each product and see which one has the smallest difference. So for the first one, 2 times 18, we have 2 and 18. That tells us the difference will be 18 minus 2, which is 16. Next, we have 5 and 15. The difference will be 15 minus 5, which is 10. And then, for the third one, we have 13 and 7. The difference will be 6. Last but not least, we have 14 and 6. The difference will be 8. So, in conclusion, we can now claim that among these four numbers, 13 times 7 will be the largest. Next, we will have 14 times 6. And then we will have 5 times 15. Last but not least, we have 2 times 18. Good. So, this is the high school algebra part. How are we supposed to check that this idea is actually true? Here comes in the calculus idea. Let's generalize the problem a little bit. Instead of saying that we have a fixed number 20, we will just say that we have a fixed value k as the sum, so that the two numbers that we're going to multiply will actually have the sum equals to k. In other words, if I call the first number a and then the second number to be b, we have the condition that a plus b is equal to some fixed number k. Then what does that do? Now we can try to choose the second variable b and write it in terms of a. And at the same time, we will just replace the a by a new variable x, so that we have x for the first one. And then for the second variable b, we are now going to substitute in to get that b is equal to k minus a, which is x, so that b is going to be replaced by k minus x. And now we want to find out that why it is true when these two values are the same will give us the maximum value. How do we do that? Since we're taking the product, let's call this a function y, or we can call it f of x, which is equal to the product of a and b. So in this case, we will have x times b, which is k minus x. So before we jump into the calculus part, we can actually think of how the graph of this function will look like. In fact, we will have something like this. So here, if we assume that k is positive, then one of the fixed point will be here, or one of the solutions will be here at the origin. Then if k is positive, then we will have something such as this. Let's call it k positive, or k1. Then the other solution of this function will be at this point. Moreover, this is a second degree function. In other words, this is a quadratic function. So, how would the graph of a quadratic function look like? It looks like a parabola, where since the leading coefficient is -1, it means that this parabola is going to open down. So it will look like this. Similarly, when k is negative, we're going to put the black point here, this solution on the right, and put it on the left. Again, that's because we want to find the solutions of the function. Then, how would the graph look like? The graph will now look like this. Great. So, knowing how the graph of the function will look like, now we can actually jump into the calculus part more precisely. We would just jump into the derivative part to see how it can help us getting the idea here. Okay, so from the last board, we actually saw how the graph would look like, and technically we should be able to claim that we would get the largest product whenever the graph hits the peak, where the peak is actually when the A value is equal to B value. In other words, X is equal to K minus X, or to be more precise, X would just be K over 2. So how do we check this idea? We can use calculus to help us, or again, we can use the derivatives to first derivative to help us proving that this conclusion or this assumption is true. So here we go. We already have the function y, which is f of x, is equal to the product, and we can multiply it to get this. So if we take the first derivative with respect to x, of course, we will then get negative x squared. The derivative of it will be 2x. Again, we'll just use the derivative of power function. We drag the power down into our coefficient, and then for degree itself, we're going to subtract it by 1. Then for the linear term kx, k is a constant, so we're going to do k times x and take the derivative of it. We have x to the first power, so bring it out, which is multiplied by 1, and then we'll minus 1 power, which gives us x to the 0 power, or just the constant term, 1. So we see that after we take the first derivative, we will be able to find the relative maximum or relative minimum. We don't know what that is yet. So how do we do it? First, let's find out where the relative extremum is at. By doing so, we will need to set the equation equal to 0 to solve for x. And if we set it equal to 0, of course, we get k equals 2x, and divide both sides by 2, we get x equals k over 2. So we just check that we will be able to get relative extrema or relative extremum at x equals k over 2. Now, of course, what would that value be? It doesn't really matter, because this is not the key point for what we're trying to do. But how do we know that that is in fact the maximum? We need to take the derivative, of the function one more time. Meaning we're now going to take the second derivative of the original function. So we have y double prime, which is equal to f double prime of x, equals, now we're going to take the right hand side and take the derivative one more time. So for the linear term, we have negative 2, which is the coefficient, times x. And again, what's the derivative of x? It's just 1. So we have negative 2 times 1. Last, we have the constant term plus k. What is the derivative of a constant? 0. Again, we can think it like this. This is equivalent to k times x to the 0th power, because it's a constant term. And we'll say that a constant term is just the variable with 0th power. Then if we use the derivative of power function, we will bring the power or the exponent 0 to the front and multiply it with the coefficients, so that we actually get 0 times k. And then it doesn't really matter what the rest would be, because we're now having 0 times something. So this would just give us 0. So it means that our second derivative is in fact a constant, negative 2. And clearly -2 is negative or less than 0. What does that do to the graph? Now we can actually make a table here. Let's do it on the right hand side. So in this table, we're going to list out some of the key points. So first, on the first row, we'll put the x value. Second row, we're going to put the first derivative, and then second derivative. Last but not least, we'll just put the y value in. And again, you don't have to follow it this way, but this is just my personal habit, so that we can keep track of everything that we want to list out. Now, what should we put here? Well, remember we say that this original function has two solutions, or two roots at 0 and k. Next, we also have this specific value, k over 2. So now we need to split it into two cases. First, we will assume that k is greater than 0. And I'll talk about a third case separately later on. So when k is greater than 0, we see that 0 between 0, k over 2, and k will be the largest, and 0 will be the smallest value. So in this table, we will just put it in an increasing order, similar to the number line, so that now we can actually do the following. We'll have 0 here, we'll put k over 2 here, and we'll put k here, and then the dot 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 means that everything else in between or after or before. Okay, and now keep in mind that we know some of the values. For example, when x is equal to 0, we know that 0 is a root, so y is equal to 0. Similarly, we get y equals 0 when x equals k. Next, we also know that y prime is equal to 0 when x is equal to k over 2. So we'll just fill it in here on top, not in the third row. Good. Then what should we do next? Now we gotta fill in the rest. So as we already know from the last statement, y double prime is always negative. So we can just put negative here to keep track that we always have negative value in the second derivative. Then now we can fill up the y prime here. In other words, we're going to fill in the second row. What do we do? For example, let's pick x equals 0. If we pick x equals 0 and substitute into our function, we will be able to get that y prime is equal to negative 0 or 0 plus k, which is k. And since we claim that k is positive, we now get that this part is positive. And similarly, if we put in x equals k, we will be able to get that y prime is negative. And then since this function is continuous, we know that it has to be the same sign until it hits 0. Good. Now, here, we want to find out whether we will be able to get the maximum or not. So we're going to use the two rows in the middle to help us determine the shape of the graph. When y prime is positive, we know that the function is increasing. It's going to give us this. Where y prime, or the first derivative, is less than 0 or negative, we know the function is decreasing. Next, what does the double prime do? Well, it tells us how it curves the function. So, if the second derivative, or y double prime, is greater than 0, which is not in our case, but I'll write out anyway, this is going to give us a graph that looks like an open up shape. like this. So it could go downward, it could go upward, but it's always a U shape. If y double prime or second derivative is less than 0, it's going to give us an upside down, or in kind of like an N shape. What does that do? Now we can combine the two conditions that we have to see how the function is going to curve. For example, if we have here plus minus, this is going to tell us that the graph is going up, but it's also bending downward. So we're going to take this and then the first half part. So we're going to get the function that looks like this. And similarly, here is still the same. And keep in mind, this 0 is not going to affect the change. That's because this is only telling us whether the value of the y value of the function is going to change the sign or not. And in other words, if it's going to pass through the x-axis or not. But it's not going to affect the shape of the function itself. So if we continue, we'll see that for here we have minus minus. This is going to say that the graph is going downward, and then it's still pointing more downward. So we will take the second half case, which is here, and claim this way, like this. So if we combine all these informations here, we will then be able to tell that this right here is in fact the relative maximum. Right. I did say that it's relative. I didn't say that it is the maximum of all. It's not absolute maximum yet. But in here, we can claim that it's a relative maximum because of the shape of how the function turns. So here, in the closed look, we'll have something like this going up until it hits this x value. And at this, after this x value, it starts going down like this. Meaning, at the x value, right here, is actually the highest point around itself. In other words, it is relative maximum because in the closed look of this graph around this point, there's no other point that we can find that is higher than it or have a larger y value of it than it. So now we can say that this is a relative maximum. How do you know that this is the absolute maximum? Well, again, we can just go back to this here and think of how the graph will look like. Since we're saying that this point is a relative maximum, we will get something right here. Now, if we combine these, before this point, everything is still going up. So we can just extend it like this. It's going up. And this is just saying that this is going even faster than here. And then here, we can just say that it's dropping faster, like this. So eventually, we still need to use a graph to take a look whether we get the absolute maximum or not. But from the graph, we see that there is no point that can be higher than this point up here. That's why we'll be able to claim that we'll get the maximum value of the products if the two values that we choose, A and B, are actually the same. Okay, so this is the part when k is greater than 0. I'll leave the other part for you guys to check, which is, yeah, k is less than 0. So for the last case, when k is equal to 0, we can just use a similar argument, but then we will see that these 3 points will actually merge into one, so that we need x equals 0, or in other words, a and b are both equal to 0 in order to get the maximum value. So this is how we can use calculus to help us analyze some problem that we have actually seen probably when we're in high school or in lower level math class. And this will be able to give us a complete answer that why those ideas are actually true. So this is quite long. Now, one more problem that I'll set up for you guys. Suppose that we still have a fixed k value, but this time we actually have three different numbers, A, B, and C, such that the sum of these three is equal to k. Prove or disprove? Disprove that the products will be maximized if and only if, no, I shouldn't say if and only if. I'll leave you guys to think about. If A, B, and C are the same value. So in this case, since these three are the same, I'll just give you another step right here, which means that they will be 1/3 of the sum, k over 3. Good. So notice that this problem here that I give you guys is actually one direction, not both directions. This is not biconditional. So you just need to show that whether this is true, or if it is not true, please give a counter example to show that why it is not true. That's it. Pretty cool, huh? So most of the time when we think of some high-level math, we actually might think, well, at least for most people, they might actually think that why we should actually learn it is not useful, or we're not going to use it in our life anyway, or for later on use. But if we actually try to think back some of the problems that we have learned when we were young, such as in elementary school or even in before college, okay, we will still be able to actually use the knowledge that we have learned in high-level math to help us analyze and actually find out a proof of why the things are true, or maybe why we might actually think true, but it's not always the case. Okay, so I hope you enjoyed this video. If you didn't subscribe to my channel, go subscribe so that you will always be able to find all my other videos, and also turn on the notification so that you won't miss any of my new videos either. And again, if you have any ideas of the two problems that I left here, please leave your comment below so that I know what you guys think. I will see you guys next time.